Babies, how we doing? Welcome to our next video lesson on sound. Today we're actually going to get into a lot of meat and potatoes on some of the special phenomena with sound and where sound, I guess, becomes unique in terms of a type of wave. And what we're going to kind of relate to is what we talked about in our basic unit of waves of interference. So remember, interference is when two waves are interacting with each other within the same medium. So we looked at, for example, the interference of transverse waves, where we would have crests meeting crests, or troughs meeting troughs, or potentially a crest meeting a trough. And we talked about two types of interference patterns, what was called constructive and destructive interference. So constructive is when they were always the same phase. So whether it was two crests or two troughs meeting together, but anytime they were the same phase, they followed what's called the superposition principle, where the amplitude of each wave would simply add together to form a resulting wave that is equal to the sum of both those amplitudes. So for example, both these amplitudes are 1, so the resulting wave would have an amplitude of 2. Same thing here, this would be -1, so they would have a resulting amplitude of -2. And here we would have destructive interference, which was the second type of interference we looked at, where you would have a crest and a trough meeting together, where they would be the opposite phase. In this case, based on the superposition principle, if I had a +1 amplitude and a -1, well, those two numbers would add to 0. So what ends up happening is the amplitude gets smaller. So in terms of sound waves, because they are waves, can interfere constructively and destructively. Just to kind of give you guys a little simulation here, you can see, imagine now instead of crests and troughs, remember we have compressions and rarefactions. Compressions are the particles of the medium when they're very close together, and rarefactions are when they're spread out. And again, this is because sound waves move differently. If I have, let's say, particles within a medium, if the wave is traveling from left to right, these little particles are going to vibrate back and forth within the medium. And anytime you have all those particles near each other, again, you're going to have those compressions, which you'll see in this little simulation, and the rarefactions where they're spread out. So notice sound waves can interfere constructively and destructively as well. Just like we talked about when we see two sound waves, or two regular waves, where we had two crests meeting each other. Here, when we see two compressions, you will see kind of the darker spots. So again, when two compressions meet up, they'll form a more intensified compression. When we would see two rarefactions meet up, it would be a more intensified rarefactions, meaning less particles in that space. And then the same thing would be true with destructive interference. If at any point they would meet out of phase, so a compression would meet a rarefaction, it would essentially cancel each other out, and there would be no compression or rarefaction at that point. It would just be at its regular position. So sound waves can interfere constructively and destructively. Now, what might this look like? So take constructive interference, for example. So what I'm going to do is I'm going to play a sound for you. This is going to be a sound. It's 440 hertz. Okay, might be a little bit annoying, but just listen to the sound. And what I'm going to do is I'm going to play another sound with the same exact frequency, so they are perfectly in phase, and listen to what happens. Okay, so again, listen to what happens when I play the second sound. Okay, so when you hear the first sound, again, you can hear that frequency, but when I started to play a sound of the same frequency, you can kind of still hear that undertone, but at the same time, you'll notice that the sound got louder, that if we have constructive interference, you're going to hear a more intensified sound. So think of like the decibels is going to increase. Now, destructive interference is hard for me to simulate to you guys in a video lesson, but destructive interference can occur. It's when sound waves completely cancel each other out. So an application of destructive interference might be, for example, like anytime you hear like noise canceling headphones, okay? What happens there is what they're doing is those headphones are technically generating a sound wave that is going to eliminate some of the noise that would be heard outside of those headphones. So it uses a sound wave to destruct any sort of noise that's outside while it doesn't affect anything inside the headphone. So again, sound waves act just like transverse waves in that they can interfere constructively or destructively. Now, another special phenomenon that occurs is when sound waves interfere, but they don't interfere perfectly, okay? Meaning that you don't get perfect constructive interference or you don't get perfect destructive interference, so something in between. So imagine, for example, you have the red and the blue wave. So let's say that I have the blue wave meeting here, and then the red wave kind of, oopsies, no, it's not red, but the red wave kind of, they don't meet perfectly in phase. So where I have my crest right here, the crest here might be shifted. So they're a little bit out of phase. What happens anytime sound waves are a little bit out of phase, they create what's called a beat. Okay, now a beat, essentially you can see this here in green. You have the red wave and the blue wave, not perfectly in phase. There are positions along this path where you see constructive interference and positions where you see destructive interference. And notice the green pattern down here. What ends up happening is they form a resulting wave that has a very small frequency. When you have the points here of constructive interference and the points here of destructive interference. Now, I want you guys to listen to this. I'm going to play a frequency of 440 hertz, and then I'm going to play a frequency of 442 hertz. Okay, so let me write those down. 440 hertz compared to 442 hertz. And I want you to listen to what it sounds like. So here we go, 440. And now I'm going to add in 442. Okay, I'm going to stop those both. Now, as you heard that, hopefully you guys would think it was pretty obvious. You would hear the wah, 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 wah. Then you heard it go loud and soft, loud and soft. But that altering between loud and soft, that was occurring at this frequency here. And it just so happens that the beat pattern that you see is just simply the difference. 442 minus 440 would give you a beat pattern of 2 hertz. Okay? So for example, if I were to play 440 again, but now instead of 442, let's say I play 444. I'm going to increase it just slightly. Notice how the frequency gets bigger. I'll go up to 445, 446, 47, 448. And again, going louder and louder. So that is what's called a beat frequency, is anytime two sound waves don't interfere perfectly in phase. If you ever hear that phenomenon where sound goes wah, 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 that's called a beat frequency. All right, a unique phenomenon that occurs when two sound waves interfere is what's called resonance. Okay, resonance is what really is the foundation to musical instruments, and it's an application of constructive and destructive interference. So what resonance is it looks at another property of an object called a natural frequency. And again, any sort of wave is created by a disturbance. So let's say, for example, I were to drop a wrench, okay? If I were to drop a wrench, when that wrench hits the ground, it's going to make a noise. Now, if I drop, let's say, a PVC pipe and it hits the ground, it's going to make a noise. Anytime I, let's say, drop any object or disturb an object, that object is naturally going to make a noise. And based on its properties, it's going to naturally vibrate at a specific frequency. That frequency is what's known as the natural frequency. So all objects will have a natural frequency. For example, and I showed you guys this video before, but let's say then that I had guitar strings. Okay, and again, guitar strings are different widths, different lengths, different stiffness to it, different tension, things we talked about before. But again, as you'll see here, the fingers plucking the strings, notice the different frequencies. All right, but fantastic. We can notice right here, you can see the different wavelengths, different frequencies, but the idea is that each of those strings, when disturbed by plucking them, are going to naturally vibrate. Now, how does this produce sound? Okay, this is where the idea of resonance comes into play, is that we design instruments such that we create vibrations that then affect the medium through. So for example, A guitar string, what we are doing is plucking a string. Now that string is not actually the thing that's making the noise. What ends up making a noise, and take for example an acoustic guitar, is we are specifically using the wooden part of this guitar. An acoustic guitar is designed to follow the property of resonance. So what resonance is that when I force a vibration, and a force vibration would be, for example, when I pluck a string. What happens when I force a vibration, sometimes it will match the natural frequency of an object, meaning when I pluck the string, it's going to make the air inside of this chamber as well as the wood itself. Everything is going to vibrate, and what happens is it amplifies the sound. You get a more intense sound. So resonance is any time a vibration or a disturbance matches the natural frequency of an object, and what you get is an amplification of that energy. Good example for resonance would be like a swing. A lot of you guys have been on a swing, so imagine sitting on a swing by yourself and you want to go further up on the swing. All of you at some point have probably learned to pump your legs as you're going through that swing. So what you're doing is you're forcing a vibration to match the motion of your swing, and that results to you going to greater heights, okay? So again, the idea of resonance is to match the natural frequency of an object, which is then going to intensify the amplitude and the amount of energy that's placed into it. This is one of the primary things within music, but this is also seen in everyday life. Okay, I talked about dropping a wrench, or on a swing set of dropping a PVC pipe. We get those things to vibrate. Well, heck, this is a video that shows the Tacoma Narrows Bridge in 1940. It's a bridge that spanned the Tacoma Narrows in Washington. What happened on a very windy day is that the wind actually matched the natural frequency of the bridge. The bridge is made out of concrete and steel. You'll see here it's swaying back and forth. But from my understanding, concrete and steel don't do that. So it just so happens that the wind matched the natural frequency of that bridge, causing it to do that. Okay, next video, this is something you guys might have seen before. That's actually something I filmed. What I did is just filled up a wine glass full of water. And if you just dip your finger in the water and then rubbed your finger around the edge, the rim of the glass, what you'll do is, because of friction between your finger and the rim of the glass, is you actually create a sound. But what ends up happening is that the vibration of that friction between your finger and the rim actually matches the natural frequency of the glass, as well as the air column between the water and the rim. It actually causes an intensified sound. So give this a listen. Now what I'll do here is I'll take a drink of water so that the water level goes down. I want you to notice how it changes in terms of sound. Notice the higher frequency. So I'm going to take another big gulp. And again, notice the change in sound. Delicious. How neat is that? I think one more time here, folks. Thirsty. So again, what happened there is that the natural frequency, I guess the force vibration of my finger on the rim was matching the natural frequency of the glass, causing that air column to vibrate, and notice that we got different sounds. And the thing to compare then is that obviously we have sound being produced in this air column, and how that compares to sound being placed on a string. You'll notice that as the water level went down, we had higher frequency. But again, what we're looking at here is interference of sound based on natural objects. All right, now our goal, again, is kind of look at how interference relates to real life. So those of you that play music and understand things about sound and music and all that should hopefully start to understand some of the things we've been talking about. So when we look at, for example, like just interference in general, constructive or destructive interference, when we look at the beat frequencies versus the resonance that occur, all those are kind of foundations to music. One of the other things we talked about were the idea of standing waves and harmonics. We looked at that in our last unit on waves. Harmonics, again, are anytime we have standing waves. So for example, our first standing wave is when we had two nodes and an antinode in between. And then when we add a node in the middle and continue to add nodes, we get different standing waves that occur at different frequencies. Well, those are known, again, as harmonics. In music, harmonics are also known as octaves. And I want to just kind of show you guys kind of where all this comes from. Is here I have a piano. In a piano, we have different notes going all the way from A to G. Okay, now why do we call harmonics octave? Is because when we look at the different notes we can play, I want you to notice, and if we count, here's A, so think of this as 1, 2, 3, 4, 5, 6, 7, 8. So notice that those two A notes are 8 keys technically apart. Okay, we have the one in the first key and then the 8th key. So they're literally 8 spaces apart in terms of our notes. Hence why we have octaves. Oct is a prefix for eighths. Now, why we have an A here and an A here and an A here and an A here is that those represent the different harmonics. If I were to play this for you guys, okay, the first A note, if I were to play that, notice a low frequency. Now, if I play the next one, you'll notice that the frequency gets higher. First standing wave, second standing wave, third standing wave, and fourth. First harmonic, second harmonic, third harmonic, fourth harmonic. We do the same thing with the B. B, again, 8 keys apart, B, B. So again, our harmonics are just the different standing waves that are representing those different notes. Then again, where that word octaves come from is basically how far away those keys are from each other. In terms of the frequencies, again, when we play these different things together for an octave, you're always going to have a frequency that's a whole number of whatever that harmonic is. So for example, if this was 40 hertz, the next one would be 80, and then it'd be 120, and so on and so on. That the frequency of those harmonics or those octaves are always going to be whole number integers of whatever that fundamental frequency is. Okay? Now, there are other relationships that we have in music. Obviously, we don't just play a single note. I'm not just going to play one key, but instead I'm going to play keys together. So, for example, I'll just touch random, okay? And you can hear how those two keys might actually sound good. So when I play different chords or different things like that, that there are different frequencies that actually sound good. And there's actually a mathematical relationship between some of these. So for example, there is what's called a fifth. Okay, and a fifth, the way I like to look at it is kind of the black keys. Notice that you have a pattern of 2, 3, 2, 3, 2, 3. It's kind of unique that 2 and 3, what do those add up to? Well, they add up to 5. So a fifth is anytime you have a ratio between the frequencies of 3 to 2. So for example, I'll just pick a simple one. You could have a relationship of 300 hertz to 200 hertz. That would simplify down to a 3 to 2 relationship, okay? Those on a piano might be seen as the black keys on top. So for example, if I play the one here, okay, between the C and the D, that's called the C sharp or the D flat. Now if I were to count 5 keys over to here, notice that I will have C sharp, D flat, C sharp, D flat. And again, if I go 5 keys over, C sharp, D flat. Notice the different frequencies. So it's interesting how you get these different mathematical patterns between the frequencies of different sounds we can play. And this is how we get into like the foundations of music theory. So for those of you that might have studied that or know that, okay, that's kind of where all this is founded. Now there are sounds, again, that sound good, and there could be frequencies that don't sound good. So things that sound good is what's called consonants. Okay, those are sounds that actually sound pleasant to the ear. But then there's also some sounds that do not sound good together. It's called dissonance. Okay, and that's any two sounds that would not have something good. So they would follow like a random pattern here, like 37 to 20 is a ratio of their frequencies. Okay, so for example, they might have a frequency pattern of 370 hertz as a ratio to 200 hertz. Okay, so those two sounds, if we were to play them together, probably wouldn't sound good. Kind of show it to you, grab a listen. Here's 370 hertz. And here's 200 hertz. And there's a fire truck, folks. Okay, so again, you're going to have different frequencies representing different sounds, and there's blends of how those sounds will actually sound pleasant to the ear.